Okay, I think we're recording. We're all good. All right, perfect. So yeah, so as I was saying, last time we were talking about these rotation matrices in SO3, right? And we came up with this idea that we could represent all sorts of rotations, any rotation out there using this set called SO3, okay? So represent any rotation using a matrix R in SO3. So I use this little E symbol right here for element. That means that it just belongs to this set called SO3. Okay. So what other rigid body transformations are out there, right? You know, we were just talking about simple rotations last time, like just if I'm spinning this around a single point. But what happens if I want to do something a little bit more complicated, right? Like what if I want it to be spinning and then translating, or spinning and going this way or something like that, right? We haven't actually talked about how to deal with this case yet. And this is actually the more general case that we are going to be interested in robotics, right? So how do we deal with translations? How do we deal with translations? And maybe rotations at the same time. All right. So over the course of today, we're sort of going to talk about how we can represent these translations and rotations together. We're going to talk about a couple of different methods of representing them, from just straight up matrices to exponential coordinates and screws, which sort of are another way of looking at this. Okay. So let's talk about what rigid body transformations are in general. All right. So in general, a rigid body transformation is made up of, first we have a rotation, right? Which mathematically we could think of as some matrix R in this group SO3, as we were just talking about. And secondly, we have a translation. Okay, how can we think about a translation, right? So if I take like my pen over here and I just move it in this direction, right? We could just use a vector to track where it's going in space. So maybe we're going to call that vector P, and that's going to be in 3D space since we're working in full 3 dimensions over here. Okay, so we say P is a vector in R3, R is this matrix in SO3. And using these together, we should be able to describe every sort of rigid body transform out there. Okay. So how do we actually get to doing this mathematically? What are we going to do? So in general, something that we like to do is we like to represent these rigid bodies using coordinate frames, right? They give us a good way to keep track of where these rigid bodies are and sort of figure out where all these points on these rigid bodies are moving, right? Like if we attach a coordinate frame to here, then I know the position of this in that coordinate frame. When I move it over here, I'll be able to figure out where that is with respect to my original, right? They give us this really convenient way of dealing with motion. So let's think about these rigid body motions in the context of coordinate frames. So coordinate frames and rigid motions. All right. So let's think about a coordinate frame that gets both rotated and translated, right? Now we're stepping it up a notch. This is this case that we want to be looking at. Okay. So let's start out with just our basic frame, which I'll call frame A. Okay. And then I'm going to have this rotated and translated frame over here, which I'm going to call frame B. All right. Now let's suppose that I have this point over here in frame B called QB, and I want to figure out what QB looks like from frame A, right? So QB is all the way over here, and it's also with respect to a different set of axes. So there are two things that we have to keep in mind, right? First, we've got to align those axes, and then we actually got to shift this entire coordinate frame over. So we're going to see how we do that in just a second. But let's see how we can break this down, right? So if every sort of rigid body transform out there is made up of a rotation and a translation, we're sort of going to think about them in those two parts, right? It's sort of easy just to break it up into those simpler parts. So first, I'm going to say that I have some sort of translation that is going all the way over here. I'm going to say the vector pointing from the origin of frame A to the origin of frame B is going to be this vector PAB, right? And that's a 3D vector because we're working in 3D space. All right. Now we know that we could represent these rotational orientations using rotation matrices, right? So say I'm going to have this rotation matrix RAB, right? And that's going to take these points in frame B and rotate them so that they at least align with the axes of frame A, all right? So how do we actually represent QB in frame A, right? What's the process for that now that we have this additional translation? So it won't actually be much more than what we were talking about before. It's a pretty simple addition. but let's just go through it anyway. We'll do the due diligence and see what happens. Okay. So first off, what I'm going to do is I'm going to just apply the rotation matrix. Okay. That's something that we've done before. That's a pretty familiar operation. And what point are we going to get out? Let me just call it QA prime. And QA prime is equal to RAB times QB. So what is this QA prime doing, right? So what QA prime is doing is it's taking this vector, QB, and it's representing it with respect to a frame that's aligned with the axes of frame A, but that's positioned at the origin of B, okay? So we're just going to be rewriting it with respect to something that looks like this, okay? We call that frame A prime. So we've correctly aligned ourselves with frame A now, but we're just not in the right position, okay? So QA prime is just what this looks like from this blue A prime frame over here. All right. So we've represented it in something that's aligned with the axes of frame A. Now all that remains is just to go ahead and add on this translation part. Okay. So now we want to add the translation. And since A and A prime are shifted over just by this vector PAB, we know that QA is just equal to QA prime plus PAB. Okay. All that we're doing is just adding on that translation that we need to shift this coordinate frame. So then all up, when I go from B straight to A, let's just plug this into here and see what it gives us. So all in all, we're going to get QA equals RAB, rotation matrix from B to A, times QB plus the translation between the two of them. All right, great. So we now have this representation of QB as seen from frame. Okay, does anyone have any questions about how we got here or any of the steps that we took in the middle? Yeah. Right.
That takes us from. Oh, so it's okay. I guess I want to understand. I want to understand like the line above the one you.
Like this one right here.
Yeah.
Okay, cool. Yeah, that's a good question actually. So the way that we could think about that is sort of like with the origin of these two vectors, right? So if we think about the origin of this point, right? Let me call it QA prime equals like 0, 0, 0, right? And that's as seen from this frame A prime, right? We want to represent that with respect to frame A. We know that it's not sitting at the origin of frame A, right? We know that it's sitting at this vector over here. So we have PAB. And just an example, I'll say PAB is equal to 0, 1, 1, right? Because we moved over in the y direction a little bit, we moved up in the z a little bit. So now if I want to see what this QA prime will look like from frame A's perspective, all that we need to do is just add on that vector that points to the origin, and then that'll take care of it for us. So then we'll see QA is equal to 0, 0, 0, which is our A prime vector, right? And we're adding on this 0, 1, 1. So then we find out that the coordinates of the origin of frame A prime with respect to frame A are just 0, 1, 1. Does that make sense? Okay, sure, yeah. All right, do we have any other questions before we... Let me scroll up a little bit. Okay, cool. Just gonna have a drink of water. Thankfully, it is cooling down in here a little bit, I think. All right, perfect. So where do we go from here, right? Are we done? Can we just call it a day and like end the class right now? Unfortunately, we gotta fill up a couple weeks, so we're gonna make things a little bit more difficult for you guys. But really, why do we want to move on from this, right? This seems like a perfectly good representation. It seems like something we might be happy with. Why is it not good enough for this class? Well, what we want to do is we want to be able to represent this entire thing just as a single matrix transformation, all right? So I want to represent the process of going from QB to QA as a single matrix. Now, why do we even want to do that, right? Why does that matter? Well, when we start adding like a lot of joints on our robot arms, right? We don't want to have like all of these RAB, QB, PABs floating around, right? We just want to have a single matrix multiplication that we know will get us from frame A to frame B to frame C and so on and so forth, okay? So if we have a single matrix, everything is going to be much, much easier for us to deal with in the long run when we start dealing with these more complicated systems, okay? So how do we actually represent this as a single matrix multiplication from QB to QA? What does that look like? So there's going to be sort of a sneaky trick that we use to do this. And it has a special name that we'll talk about in just a sec. But for now, I'm going to do something a little bit strange. So we're going to take a look at this expression right here, and I'm just going to put a 1 underneath that. Okay, I'm going to put that in a vector. Right, so beneath QA, I'm going to add a 1. And I'm just going to add RAB QB plus PAB. And I'm going to put a 1 beneath that, right? And we know that these are still equal, right? Because this is just the same thing as that. And we showed that this and this are the same above, and 1 are the same, right? So these vectors are still pointing in the same direction. They're still equal to each other. So that's not a problem. But why don't we go ahead and put this 1 down here? What's this going to do? Well, now, here's what I'm going to try and do. I'm going to try and factor out a QB from this expression, okay? But I'm not just going to try and factor out a QB. I'm going to try and factor out a QB and a 1, okay? And we'll see why that is in just a second. So what we're going to do now is we're going to look for the following matrix. So we want to figure out some matrix that will take us from QB with this 1 underneath to QA with this 1 underneath, right? And the reason that we do this is that, this is a pretty easy way of dealing with, this sort of PAB that's floating around up there, okay? We want some way to be able to add this onto it without having this whole complex transformation of PAB. Adding a 1 is pretty much the simplest thing you can do to a vector. So that makes it kind of nice for us. But what could this matrix be, right? So if we look at the first column, we see that, all right, we want to have this RAB times this QB, and we have QB in the first position up here. So what I'm going to do is I'm going to put this RAB up there. But then we're also adding on this vector PAB, right? And we're adding 1 times this vector PAB. So what I'm going to do is I'm just going to put PAB in that column right there. But now we still have a little bit of bookkeeping to do in the bottom row down here, right? We still have this 1 that's left over. So how do we ensure that we're able to get that in? I have no idea. I'm sorry. So we're going to put a 0 right here to make sure we're not adding any extra QBs. And then we're going to have a 1 right there. So what this gives us is we have we have QB times RAB, which is what we want. We have 1 times PAB, which is what we want. Then at the bottom, we have QAB and 0, right? We don't want to get any extra QBs. And then we have 1 times 1. So then we get QA and a 1 underneath. All right? So what we've essentially done over here is we've just found a matrix that gives us a map between these very, very slightly modified versions of points, QA and QB. Okay? So this is almost the same thing as giving us a map between QA and QB. Just now we've added this extra 1 that helps us with this bookkeeping term of this translation over here. All right? And this is something that's pretty important to us. It's going to make our lives a lot easier when we're dealing with these matrix multiplications. So we get this idea of adding 1 underneath the vector, the special name of homogeneous coordinates. Okay, so if we have a point like P, and that point is just like 1, 2, 3, for example. If we want to find the homogeneous coordinates of P, all that we're going to do is just stick a 1 underneath there. It doesn't matter what P is, as long as it's a point, we're just going to put a 1 underneath. Okay, so I'm going to denote that with P with this bar above is 1, 2, 3, and then 1. Okay, so whenever you see that bar above the letter, that means that we're talking about these homogeneous coordinates. So we'll have this extra 1 added underneath. Okay, so over bar equals homogeneous. And in general, I'll just, say this out loud as like P bar or something like that. Okay. All right, cool. So using this notation, let's just rewrite this real quick and just make sure we know what we're talking about. All right. So this is QA with a 1 underneath. So I'm going to call this QA bar on the left-hand side. And it's equal to this big matrix, right? RAB, PAB, 0, 1 times QB with a 1 underneath. All right. So that is QB bar. So what this matrix is doing in the middle is it's finding a map between QB in homogeneous coordinates and QA in homogeneous coordinates. All right, perfect. So what does this matrix actually tell us in general for a rigid body transformation? Well, you might remember from all the way in the beginning of this problem, we were talking about a transform between 2 frames, right? So we had frames A and B over here. We have this translation between them, and PAB, and we have this rotation RAB between them, right? So this is the most general case possible, right? We have a rigid body rotation and we have a rigid body translation. And just using this matrix on its own right here, we've been able to encompass everything that's happened in this transformation of these frames, okay? So for that reason, we're always going to use matrices of this form that you see right here to represent rigid body transformations, okay? They have the rotation that we need right there, RAB. That gives us the correct orientation. And they also have the translation that we need, PAB, to give us the correct position in space, okay? So since this matrix summarizes everything that we need to know about a general rigid body transformation, we're going to give it a special name, all right? We're going to call this matrix like a GAB, all right? And you can think of that G as like standing for general, since this is the general case. And when we write this all out, we have QA bar equals GAB times QB bar. All right, perfect. So this is how we transform between two different frames in the general case of rigid body motion. All right, so let me go ahead and just summarize. Summary. What did we learn right here? So we had a matrix of this type, right? RP01, where this is a rotation matrix in SO3. This is a point in R3 that does our translation for us. And this was able to give us a general rigid body transformation. Okay. So just like we defined SO3 as the set of all rigid body rotations, we're going to come up with a name for the group of all of these matrices as well. All right. So we're going to say SE3 equals the set of all matrices of the form RP01. All right. Where R is a rotation matrix, R element SO3. So that's a rotation matrix. And P is just a vector in R3 that does our translation. Okay? So that is our translation. Okay. And because it has this property where it has this rotation and it has this translation, we say FE3 is the space of all general rigid body transforms. Okay, so as long as it's a rigid body transform, we're going to be able to represent it using this form. Okay, yeah. Oh, yeah, sure. Is this further? Just tell me when. Down. Okay. Down. Right. So P is in R3. Yeah. Why is P not? Oh, yeah, that's a good question. So P is just this translation from A to B, right? So if we want to figure out the position of something in space, we specify like its X, Y, and its Z coordinates, right? And if we just stack X, Y, and Z on top of each other, that's just going to be a vector in R3. So you can think of PAB as the coordinates of like the origin of this frame right here in this frame. So we only need 3 numbers to specify that versus SO3, which is actually a 3x3 rotation matrix. Yeah. Cool. Yeah. Is P written with respect to like the rotated? So P is written with respect to A. So it's written with respect to the one that we're trying to go into.
For P, you said that it's the point for translation, right? So it is a point, and it's a point that we look to see if there has been a translation.
Yeah, sure. So if P is 0, that means that it's just a pure rotation that's occurred.
Okay.
Yeah, that means that we're not bringing our frame in. Okay, cool. All right, yeah, so let's just do an example real quick and we'll see how these matrices come together and what they look like. All right, so example, let's say we have frame A over here. This is our favorite setup, frame A. And then we have this other frame, frame B up here, okay? It's going to be rotated slightly. This is frame B, frame A, and we have this vector. Yeah, let me call it R equals 0, 1, 1. All right. So relative to frame A, B is shifted by 1 along the y-axis in this direction and in 1 along the z-axis, like up this way. Okay. So this is XA, YA, and ZA. And this is XB, YB, and ZB. Just to clarify, YB is pointing into the page in this case. Okay. All right. So we want to figure out the transformation GAB, which is in this set of all rigid body transformations, right? What does that look like? So we know that this will be of the form just RP01, right? Based on that definition. So we're going to have an RAB, we're going to have a PAB, and then a 0 and a 1. So if we want to find this matrix GAB that's taking us, between these two frames, all that we need to do is just solve for these small parts inside here, okay? And we could just do that step by step, right? There's no real formula for doing this. So we're just going to choose to do rotation first and then do translation afterwards. We'll just get the trickier one out of the way. So how do we deal with the rotation matrix between A and B? Now, when you're looking at this, just remember that this is the same as any other rotation matrix that we've talked about. There's nothing special about it just because it's sitting in this GAB matrix. We find it the exact same way that we would any other rotation matrix between two frames that have been rotated. Okay, so let's take a look at the orientation of these frames with respect to each other. So we had XA, YA, and ZA, and then we had, sketch this out once more. This is XB, YB, and ZB. So how do we find the rotation matrix RAB? Well, what we're going to do is we're going to go back to the definition of a rotation matrix. And that tells us that the first column of this rotation matrix will be the first basis vector of frame B as seen from frame A, all right? The second one is the second basis vector, YB, as seen from frame A. And finally, we're going to have ZB as seen from frame A, okay? And this is a good method to use. This definition is very handy, especially when we have simple rotations, okay? So when it's very easy to tell like what these vectors look like from frame A, this is going to be something that's kind of helpful for us. Just really helps us pick it out by inspection, okay? So let's try doing this process. Let's see what XB looks like from frame A. So if we were just looking at the vector that's pointing, like in this direction along here, which is XB, what does that look like in frame A? Well, that just looks like YA, right? So that's going to look like the vector 0, 1, 0. That's going to be our first column of the rotation matrix. Now, what about YB? Let's move on to the next one. Well, YB is pointing opposite to the X direction from frame A, all right? So it looks like the negative X vector. So it's going to be negative 1, 0, 0. And finally, the Z-axis we see just stays the same, right? Like this is still pointing up in both of these frames, all right? So it still looks like the Z-axis, 0, 0, 1. And that's how we find our rotation matrix, right? So you could see that when we have these very simple transforms, we can really just pick it out visually and just see where these vectors are with respect to this original frame A, okay? So we found RAB, right? That's all good. Now we just need to go ahead and find this PAB over here. What is that equal to? Well, PAB is even more straightforward than RAB in this case, right? This PAB is just what tells us how far we need to go and in what direction to get to our new frame. So PAB is actually just equal to this R between the origins. All right, so PAB is equal to 0, 1, 1. PAB equals 0, 1, 1. All right, so we have everything we need. We're just going to go ahead and put it in our format. GAB equals RAB, PAB, 0, and a 1. All right. Now, this is using a block matrix form, which might seem a little bit strange if you haven't seen it before. So this is actually referring to an entire 3x3 matrix that we're sticking in here. This is like a vector, right? So what does this actually look like when we plug in these matrices and these vectors into this form? Well, we're going to end up with the following matrix. So first off, we're just going to copy our RAB into the upper left corner, all right? Since we have it in the upper left up here. And I'm just going to go down 0, 1, 0, negative 1, 0, 0, 0, 0, 1. All right, cool. That's our RAB. We put that in. All right. Now we're going to do PAB. We have a 0, 1, 1 in the upper right corner. So I'm going to do 0, 1, 1. And finally, we have this 0 and a 1 down here. And this just tells us that beneath RAB, we're going to have all zeros, 0, 0, 0. And beneath PAB, we're just going to have this 1. All right. So this is what our final answer ends up looking like for this case. So we have GAB is this big 4x4 matrix. Okay. So in general, when we're dealing with elements of SE3, these general rigid body transformations, they're going to be 4x4 matrices. All right. So when you're looking at that definition, RP01, just remember, these are not real numbers, right? This is a matrix, and this is a vector, all right? And that's what ends up giving us this 4x4 shape instead of a 2x2, which is what this might look like, upon a first inspection. Okay. How do we feel about that problem? Good. Alrighty. Sweet. Let's see. Okay, we can come back to that later. All right, very cool. So let's just go ahead and summarize. Summary. Let's see what we learned so far. Okay, so we can represent rotations and translations using matrices in SE3. And those matrices will look like RP01, and that's going to be a real valued 4x4 matrix. So this R right here is just the rotation part, and then this P right here is just the translation part. All right. Now, how do we actually use this matrix in practice? What does that look like? Well, if we have a point A in finite homogeneous coordinates that we want to find, we can figure out what it is just by doing GAB times the homogeneous coordinates of that point with respect to framing. Okay. All right. So that's what we have to cover about SE3. Do we have any questions about just this SE3 stuff before we move on to twists? Or how do we do? I'll give you guys a moment to copy it down. Some of yours already. Let me know if you need me to scroll up or anything. I'm just going to start saying this one. Okay, cool. So let's go ahead and talk about twists. So our process for SE3 is going to very, very closely mirror what we did for SO3 last time. Okay, so recall that after making a definition for SO3, what do we do next? Well, we did a lot of things, but does anyone have any idea like the big next step that we took after coming up with this basic representation of rotation matrices? Yeah, exponential coordinates, right? So we went to exponential coordinates. So we noticed that these matrices, like R and SO3, these weren't just basic 3x3 matrices with 9 elements, right? They had constraints on them. And those constraints meant that we were able to find a much more efficient representation of rotations, right? So we can represent with only 3 parameters, right? We were able to parameterize the space of rotation matrices by coming up with these exponential coordinates. So we said for every rotation matrix, we could represent that as e to the omega hat theta. Now, just to review what that means is if we have an axis of rotation omega like that, and we have this rigid body over here that's just rotating about this axis, an angle theta. The rotation, being like rotated about this axis by an angle theta is given by this e to the omega hat theta. Okay, so rotates about omega by axis by angle theta. Okay, so that's what exponential coordinates did for us in the case of pure rotations. But now we're gonna want to go and do the same thing for this more general case. Okay, so now we have translations as well. How are exponential coordinates going to be able to deal with that? Can we actually use them? If you turned it over to yesterday, but that is the case. We can use them. So spoiler alert. But how do we do the same thing for SE3? Right? So we have these matrices, R0, 1, which are in the set of 4x4 matrices. So they have 16 total parameters. Right? Since we have 4 rows and 4 columns, we have 16 elements in this matrix. But can we control each of those 16 elements independently, right? Or are there constraints? Right? Are there constraints that make us able to represent this 16 element matrix with a smaller set of numbers? All right, well, let's sort of think about it in terms of an actual rigid body, right? So if I have, let me use my water bottle instead. So if I have this water bottle, right, we know that it has 3 rotational degrees of freedom, right? We're rotating it about this axis, and about this one over here, right? Every rotation out there is going to be a combination of rotation about these 3 axes. Now, just like we can rotate about 3 axes, we can also translate about 3 axes, right? We have X, Y, and Z in space. So I can move it this way, move it that way, or I can move it up, okay? So we have 3 rotational degrees of freedom. 3 rotational degrees of freedom. I'm just going to abbreviate that DOF here. And we also have 3 translational degrees of freedom. Okay, and those are like our X, Y, and our Z axes. So if we're only able to rotate about 3 directions, and we're only able to translate in 3 directions, why do we need 16 elements, right? Like surely there's something that's a little bit more compact that will be able to get this job done for us. So if we have 3 rotational and 3 translational, then there should be 6 parameters to represent a rigid body transformation, G SE3. Okay, so we're going to try and figure out what those are. I think in this case, it's not going to be quite as simple as the one for rotations. A couple of funny terms are going to pop up this time. Unfortunately, it's not going to be quite so neat, but we will see what the 6 numbers are, and we will do our best to interpret them, give them physical meaning. Okay. So let's just summarize our whole idea, right? So if we had this, angular velocity vector omega that was able to give us like the omega hat theta, some rotation matrix in SO3, what we're going to do now is we're going to look for, instead of a 3-dimensional vector, we're going to look for this fancy 6-dimensional vector, all right? Because we have 6 degrees of freedom that we're able to control independently. And we want to be able to find that 6-dimensional vector such that e to xi hat theta will give us some transform G in SE3. Okay. So instead of having just this axis of rotation that generates this rotation matrix, we're going to have the 6-dimensional vector for parameters that we don't really know the values of yet, that when we take the exponential, it gives us a rigid body transformation. Okay. So we're very, very closely mirroring our whole philosophy. Sorry, I'm in the way. So we're closely mirroring our whole philosophy for SO3, right? Under this exponential, we're able to figure out a very short parametrization of these rotation matrices. Now, under this mysterious new vector psi, we're going to be able to figure out what every rigid body transformation matrix is. Okay. So I'm just going to have a quick note about this guy right here, which is like xi. It's spelled xi. Like I know there's like a lot of different pronunciations of it, but I like saying it like xi like that. And I know like everyone always draws it really quickly in lectures like that. Yeah. So it's kind of hard to figure out like how to actually draw it. So like I usually just start up there and then just loop around and then loop around again, and then you just finish off with the squiggle at the bottom. So if you want to just like practice drawing this on for a second, then go for it. If you want me to do that again. Okay. Yes. Yeah, sure. I know, like I remember I was in lecture like last year, and I just watched them just go like, and I was like, what was that? And then that was the rest of the semester. So yeah. Oh wow, I don't want to stop the magic if you want to go for it. But yeah, sure. Yeah. Yeah, so don't mix this up with zeta. That's another Greek letter that also kind of looks like a squiggle. It looks like that. That's a different letter. So xi is this one that we're talking about here. And then that's a zeta. Zeta. All right. Yes.
exponential kind of came out of the blue. It's just like, oh, here's exponential.
Yeah, yeah.
Why are we using these? And we're already repeating stuff, but then how did the exponential come into play?
Yeah. So the exponential came into play like with this idea of like angular velocity, right? Angular velocity, which is this 3D vector that describes rotations. And we know that for any point, the velocity of that point is equal to the angular velocity, like cross product with like the position vector at that point, right? So we know that this is some sort of description, like the time derivative of that point times omega, or let me make that an r, equals omega cross r. And then from there, we went into the hat map, which we know is another way of writing this, omega times r. And then once we have this hat map, we know that this is now a linear differential equation, right? So we use the matrix exponential to solve it. We have r of t equals e to the omega hat times t times r of 0. And then, yeah, we were like, okay, the magnitude of omega is 1. So for every 1 second that passes, we're moving 1 radian. So we could just swap that out with the theta. And then that's how we landed up with almost that. Yeah. So now we're going to go ahead and do this entire process just for these rigid body transforms instead. All right. So let's see. Sure, let's start with translation. Okay. So we're going to split this up case by case and see if we could figure out the exponential coordinates in the case of pure translation, and then in the case of a pure rotation afterwards. And this will just sort of make our life easier for now. When we talk about the combined case with screw motion, it's going to be a little bit more complicated. So I think we'll get there when we get there, so to speak. But for now, let's talk about a pure translation. All right. And a lot of the things we're going to do with this pure translational case, they're going to seem a little silly and just like we're, adding matrices for the sake of adding matrices. But the basic idea is that we want to represent, all rigid body transformations in this form, like e to the xi hat theta, right? Because then when we're, sorry. Oh, angular velocity is a 3D vector. Sorry. I use a lot of abbreviations here. Vector that describes, describes and then rotations. Yeah, if you need any language translation, do let me know as well. My tablet handwriting is not the best. Not to say that my paper handwriting is any better, but yeah. So the basic idea is we want to be able to represent any rigid body transformation out there as e to the xi hat theta. So that way, if we have any arbitrary sequence of these rigid body transformations, we don't need to think about them as separate things. We could just think about them all as these exponentials, right? And if we're trying to compose them, e to the xi hat 1, theta 1, e to the xi hat 2, theta 2. And we could do this e to the xi hat n, like theta n. And it really just helps us keep organized when we're talking about these problems of rigid body motion. So our whole goal here is to abstract the idea of moving into this exponential. So we really don't have to worry about the actual mechanics of it, okay? We're just going to try and come up with this convenient exponential representation so we can just hide away everything that's really happening. All right. So let's talk about how we get this form for a pure translational motion, okay? What does that look like? So we're going to start out with our frame A, favorite frame, and say we have this point in frame A, okay? We have this point P of t. Maybe it's got like this little frame attached to it. It's got like a vector there and there. And we have this vector pointing to this, right? And that's our vector P of t. It's telling us where this is as a function of time. And let's say that this point is moving along this direction, some velocity v, okay? So v is pointing in our direction of motion, right? Velocity is always tangent to the path of the particle, right? And we're going to set out this constraint that the magnitude of velocity is equal to 1. Now, already you might be able to see some sort of parallel with what we were doing before, okay? So we're going to say the magnitude of this velocity needs to be 1. We have this point P moving in this direction V at 1 meter per second, all right? So how can we come up with some sort of differential equation that describes, where this particle is going in time, right? This is going to be a very simple differential equation, but we know last time by taking this differential equation approach, we were able to get this exponential. So here we'll try it again. We'll see if it gives us something the second time around. All right. So we know that the magnitude of v is 1 meter per second. We know that the time derivative of position dp dt is equal to our velocity v, right? That's just by the definition of what a velocity is. Now I'm just going to write this for convenience as p dot, just to mean your first time derivative. All right. So now, you might remember earlier, we were talking about these points in homogeneous coordinates, right? We were like, this is a really convenient way of representing these rigid body transformations as a pure matrix, okay? So maybe just using these simple points in R3 are not good enough. Maybe we should take this up into homogeneous coordinates, all right? So I'm going to add a 1 underneath each of these. But for velocity, I'm actually going to add a 0 underneath, and I'll tell you why that is in just a second. So this is equal to d dt in homogeneous coordinates of the point P1, and that is equal to v and 0. Okay, so the reason we have a 0 for velocity is that the time derivative of a constant is equal to 0, right? So that'll just end up dropping out to 0. We end up with this equation, p dot 0 equals velocity and 0. Okay, so this is now that same differential equation that's just written in homogeneous coordinates. Okay, we just added this extra dimension. We're going to see why we did that in just a moment. Okay, so let me just rewrite this out, the actual vectors. P bar dot equals v dot, v bar. Great. So now what I want to do is I want to write this whole thing out as a map. And this map is going to be from the point in homogeneous coordinates to its derivative in time. Okay, because earlier, when we were dealing with a rotational case, we found that when we got this map from the position of a point to its derivative in time, we were able to get this exponential differential equation. And this is what we're seeking again in this case. So we're really going to follow our same steps to try to replicate that process. Okay, so we're going to try to figure out some map such that p dot 0 is equal to some matrix times our point in homogeneous coordinates, p with 1 underneath. All right. So what could this matrix be? Right? Like, what is that? Well, we know that we need to have a velocity in the top row, and we know that we need to have a 0 in the bottom row. So what I'm going to do is I'm just going to say p dot 0 equals 0, b, 0, 0, okay, times p and 1, right? Because we noticed that there was no actual point p in this expression up here. So we want to knock that out, make sure that it doesn't show up. So we have p times 0. And we know that we have a velocity in there that we need to take care of, right? So we have plus 1 times v. So that's where our velocity comes in. All right. So this equation right here, just note that this is actually a 3 by 3 matrix, right? Because if we want to multiply this point by this 0, it can't just be like a 0 scalar. It's actually going to be a 3 by 3 matrix of zeros. Okay. So this right here, we're going to give it a special name because it is a map from p bar to p bar dot. All right. So we have p bar dot equals 0, 3 by 3, b, 0, 0 times p bar. And this was exactly the map that we were looking for. Remember, now we've turned this into a matrix differential equation, right? I'm going to call this map xi hat. All right. So I'm going to rewrite this p bar dot. This map xi hat times p bar. All right. And now this is just a matrix differential equation, right? We could use the exponential to solve it. And we find that p as a function of time is equal to e to the xi hat times time times our position. Oh, we should all be homogeneous coordinates times our position in homogeneous coordinates at time 0. Okay. So this is where we are in our whole process. Let me just sketch out where we are and make sure that everyone knows, what's actually going on. So remember, we have this point p of t, right? This point has a velocity v with unit magnitude. And we've just figured out how to describe how this point is moving in time using a matrix exponential, okay? So we figured out how to map from, our position over here to our position over here using an e to e xi hat times time, all right? So now I'm going to make use of this property that says that the magnitude of v equals 1. And the reason that we require this is the same reason that we required that the magnitude of omega was 1 when we were dealing with that a while ago, okay? So if the magnitude of v is 1 meter every second, that means that for every second that passes, for every second, we move, so for every 1 second, we move 1 meter, okay? So the distance we travel and the time that passes are totally interchangeable in this equation, all right? So I'm going to call theta the distance traveled. Okay. So in the case of pure translational motion, theta is always how far we're translating along this axis v. Okay, it's not an angle. I know we use theta for like angles all the time, so it's really weird to see it used for something else. But in this case, we're going to use theta for how far we go. All right. We find that p, when we're at distance theta, is equal to e to the xi hat theta times p bar of 0. Okay. And that is our final map from our initial configuration to a configuration that's been shifted by a distance theta along the axis v. Yes. Oh yeah, I'm sorry, that's a bracket. Yeah. So let me just draw that with an arrow. Theta distance drop. Yeah. So let me just clarify over here. So e to the xi hat theta is the transformation of moving distance theta in direction v. Okay. So all that v is doing is pointing us where we need to go, and all that theta is doing is just saying how far we're going along that direction. Okay. Yeah. Oh, moving. Yeah, that's a good question. So something that I want to emphasize here is v is not the actual velocity of the body. Okay. Like if I'm moving this water bottle around in time, like v is not how quickly this is speeding through space, right? What we're doing is essentially we're taking advantage of the properties of velocity. We're taking advantage of the fact that it's the time derivative of position to use it to get a convenient representation for translation. Okay. So what it is it's just a vector pointing where we want to go. And we use the fact that it's like a velocity vector in air quotes, just to end up getting that differential equation. So it's not actually the physical velocity of it. It's just a direction pointing where our rigid body will be going. Does that make sense? Yeah, sure. Yeah. Why is it that we chose to use theta as Yeah. So that's really just like the notation that the book uses. Because like if you have like a robot right here, like something like this, and then you have an arm that's able to move back and forth, right? Like we're gonna have an angle theta describing this, like the angle of that. We're gonna have like another angle theta describing where that is relative to the previous arm. And if we want to like represent everything as like e to the xi hat theta 1, xi hat theta 2, and xi hat 3, theta 3. Right. Exactly. Yeah. So we just want to stay consistent, like with this, composing transformations. Yeah. Yeah. So if we give a transformation like g equals rp01, and like R is the identity matrix, like it's a pure translation, we can actually figure out the V for the twist just by doing P over the magnitude of P. So we'll talk about that a little bit later when we do screw motion, but you're exactly right. So it's just pointing where we're going to be translating. We just need to make sure that it's going to be a unit vector so we can get that scaling between time and distance traveled exactly. Yeah, sure. All right. Yeah.
I'm not sure if you're familiar with the lecture terminology, but is the V just the omega velocity?
So is V the omega velocity? Oh, so omega is referring to an axis of rotation. So that's something that comes up in the rotational case. So in this one, V is slightly different. So it's like you think of it like a linear velocity. So later we'll be like writing twists as like xi equals like V and omega. So omega is just that other vector that we have done. Yeah, good question. All right. So yeah, let me just summarize. So for the translational case, what do we find? We found that taking e to the xi hat theta gives us a translation of theta in direction v, where this matrix xi hat is equal to the 3 by 3 matrix of zeros, 0, 0, and this direction vector. So direction or velocity. Okay. So this is what we found for this case. And if we actually go ahead and we calculate out e to the xi hat theta, we'll find that for this case, e to the xi hat theta, I won't prove this here, but it's just good to sort of see where this ends us up. 0, 0, and a v times theta. Okay, so this will give us no rotation, since this is just the identity matrix, and v times theta just means our point P will be a translation. More space. Translation of theta along v. Okay. So that is the translational case for exponential coordinates. Before we talk about rotations, how do you guys feel about this? Good. Cool. All right. Oh yeah. Sure.
Where you were saying I think it was R dot was equal to omega cross with R.
Yeah.
So omega hat is a matrix representation of the cross product.
That's right. Yeah. So omega hat equals matrix of taking the cross product with omega, right? Like if you have omega hat times some other vector r, that's just equal to taking the cross product of omega cross r. Yeah, sure. Right. Okay, cool. So let's talk about the rotational case. All right, and for now, we're going to assume no translation. And then later, we'll come back in and we'll add translation, just to finish this. All right, so we're actually going to talk about the omega and the cross product right now. So it was more forward tracking than back tracking. So let's talk about that. Let's see how it acts. All right, so we have this axis of rotation omega, right? Which is our angular velocity. And we're rotating by some theta about this. Right. Okay, and let's say we have our point P of t that we're trying to track, and a point on the axis, fixed to the axis, we'll call that point Q. All right, so just to clarify what this omega is an angular velocity vector. Okay, so the magnitude of omega will give us our speed of angular rotation. Okay, so is speed in radians per second, right? So it's how many radians we're traveling every second as we're spinning around this axis. And the direction of omega gives axis of rotation. Okay, so in this case, as with before, we're going to set the magnitude of omega is going to be equal to 1 radian per second. This is going to allow us to do that conversion between theta and time later on. All right. Okay, so how do we think about the motion of this? Well, remember, our first step is to try to figure out some differential equation where we think we can get the exponential to pop up, right? Then exponential coordinates are just going to fall right out of that. All right, so first up, we know that we could describe the velocity of this point P, right, this vector tangent to the curve, as v equals omega crossed with its distance to the axis of rotation as a vector, right? So we think of that as the vector r in omega cross r. So it's just any vector that goes from any point on our axis of rotation. We're just going to pick it as q very close to it to be convenient. And what we're going to say is this is equal to omega cross p minus q. Okay, this is just the same thing as omega cross r. Right? We're just writing it in this form for a reason that'll become convenient in homogeneous coordinates. just a little bit. All right. So what we're going to do now is the same thing as before, right? So we know we have the time derivative of this point, and we want to find a map between our point P over here in homogeneous coordinates and its time derivative in homogeneous coordinates, okay? So we're going to start out by doing that in the same way as before, right? So we know that d dt of the point in homogeneous coordinates, P1, is equal to the following. Equal to omega crossed with P minus Q and a 0 underneath. A 0 because we're taking the derivative of constant, remember. All right. So this is just rewriting this equation above just by adding these homogeneous coordinates below. Okay, so this is like P dot 0 is omega cross P minus Q 0. And just to clarify, this term on the bottom doesn't make any difference because we know 0 equals 0. We know the top, they equal each other by the definition of the velocity up here. So we know that we're all good to go on saying that these two are equal. All right. So we're going to try and extract P bar from this, because that's going to give us our map from P bar to P bar dot. How do we do that? Well, let's just try expanding this. We'll see what we get. Omega cross P minus omega cross Q, and then we have a 0 underneath, is equal to P dot and 0. And now we're just about ready to go ahead and do this extraction of this P bar. So let's try to figure out how we do that. So P dot 0 equals some matrix times P bar with a 1 underneath, right? Our point in homogeneous coordinates. Oh, whoops, that's just meant to be a P bar. And then this whole thing is P bar, all right? It's P bar dot. All right, so do we have any questions about our setup up until this point? All right, maybe I'll give you guys a second to copy down because it's something that's really writing.
No, sorry, no P bar for the one.
Oh. Yeah, so P bar is just stick a 1 underneath the vector, like if it's, just like a point in space. Yeah. Yeah, so we put a 0 underneath because the derivative of 1 is 0. Okay, cool. All righty. So let's try to figure out what this matrix might be. So first of all, let's just take a step back and look at this omega cross P, right? We know that we can rewrite that as this matrix multiplication, omega hat times P, right? Because this omega hat is this matrix of taking the cross product with omega, all right? So what we have now is we have this multiplication of P times, something maybe over here, and then we're subtracting off this other value, all right? So we're going to encapsulate that whole thing in the following matrix multiplication. P1, P dot 0 equals omega hat, negative omega cross Q, a 0 and a 0, okay? So what we're doing is we're taking this P, we're multiplying it by omega hat, and then we're adding that to 1 times negative omega cross Q. And that gives us omega hat times P minus omega cross Q, okay? So what is this term negative omega cross Q? So what is negative omega cross Q? So earlier, we mentioned that the velocity of the point, the entire velocity of this point in space, P dot, right, is equal to, what was it? It was omega cross P minus omega cross Q. So you can think of omega cross Q as a linear velocity, but it's not the entire linear velocity, it's only a component of it, right? So our total linear velocity is found by adding these two together. So omega cross Q is a component of linear velocity. Okay, and you could think of it as what's left over for the velocity after we perform this omega cross P, all right? It's like what's left over after doing omega cross P, okay? All right, So let's take a look at what we have here all up. I'm just going to rewrite this out in this form just to make it extra clear. We have omega hat, negative omega cross q, a 0 and a 0, and p bar. So what does this matrix in the middle give us? We're going to call this matrix xi hat once again. And this matrix is a map from p in homogeneous coordinates to its time derivative in homogeneous coordinates, right? So if this is a matrix and it's mapping between these two, we're just going to rewrite this as differential equation xi hat times p bar. And we know that once again, we could just solve this with a matrix exponential, right? And we get p bar of t equals e to the xi hat times t times p bar at time 0, all right? And that gives us our solution for general rigid body rotations in homogeneous coordinates, all right? Now we have one thing to add, and it's going to be the same thing as last time, which is that we assume that the magnitude of omega is 1, right? We just want it to be an axis of rotation. We don't want to be like speeding around that thing, right? So we know that magnitude of omega equals 1 radian per second. So for every second that passes, we go 1 radian. So that means that theta and time are totally interchangeable. Or in this case, theta is the angle of rotation. All right. So if 1 radian corresponds to 1 second, and theta is this angle of rotation, we just go ahead and we plug it in our final formula. We end up with p bar of theta equals e to the xi hat theta times p bar of 0. All right. And that gives us exponential coordinates for rotation. Okay. So do we have any questions about this solution? Yeah.
Yeah, so you said that theta is time. How can you swap its space dimension?
Yeah, that's a good question, actually. So let's see, what's one way to think about that? Yeah, I guess in terms of dimensions, it's not really something that's very well defined. It's more like a mathematical trick. Like now that I look at it, that's a very good point. Like you shouldn't be able to do that dimension wise, because usually when you take the exponential of something, you want that something to be dimensionless, right? So I guess in this case, we could just say that we're talking about units of time in terms of theta. So instead of actually replacing it with the angle itself, we're just
Theta of t.
yeah, we're just relabeling time as theta. We also know that it happens to be the angle that we're going around. So I guess you could think of it like 2 pi seconds, like if you're talking about the angle theta equals 2 pi. Like you could really think of theta as just relabeling time if we're trying to be consistent with our dimensions. Sure. All right. Cool. So let's talk about how we can interpret these matrices and see what we could figure out here. All right. So let's summarize what we learned about these matrices xi hat for these cases. Okay. So for pure translation, what was xi hat? So xi hat was equal to 0v 0 0. This was the 3 by 3 matrix of zeros, right? And v is a vector pointing in the direction of motion. All right. So it was this velocity that was just pointing wherever we wanted to go. And we set that the magnitude of v was equal to 1. All right. Now we know that for this case, e to the xi hat times theta will give us a rigid body transformation, right? G in SE3 of pure translation. So just remember, whenever we have e to the xi hat something, that's giving us back one of these G matrices, okay? Now for pure rotation, what do we have? Well, we had xi hat equals, let's see, what do we have? So we had omega hat, we had negative omega cross q, and a 0 and a 0, all right? Now here, the magnitude of omega was equal to 1, and omega was the axis of rotation. All right, so it was this angular velocity. All right, so what similarities do we notice across these two xi-hats, right? So here, even though we have either the xi-hat theta giving us a rotational transformation in SE3 of pure rotation, there are still some similarities that we could tell across these different xis, right? Like over here, we had a 3x3 matrix in both cases, right? Because omega hat in this cross product matrix, 3x3 matrix. And over here, we had a velocity of some type, right? Now, in this case, remember, it was this extra component of velocity, right? That helps us get our full expression for the time derivative at this point. And here, it was just this direction vector. But they were both velocity vectors, right? They were both velocity vectors in 3D space. So using the similarities between the two of these, we say that in general, for any rigid body motion, we're going to be able to define some matrix xi-hat that will follow this format. All right, so xi-hat equals, over here, we're going to have an omega hat. Over here, we're going to have some velocity. It might be our direction vector. It might be that extra component of velocity for rotation. And then underneath it, we're just going to have these zeros, okay? So just note that if you're wondering, why this actually matches up with the translational case, for translation, omega is just the zero vector. So that's why that drops out to the zero matrix, okay? So this is why this guy becomes the zero matrix for the pure case of translation. All right. So let's just think back to our goal all the way at the beginning, okay? So we wanted 6 parameters for an arbitrary matrix G in SE3. Now, did we actually find those? Were we successful? Well, just like we were able to go back from, this matrix omega hat back to our vector omega for SO3, we're going to be able to do something similar for SE3, right? We're going to be able to go from this xi hat back to some xi, whereas this was a vector in R3, this is going to be a vector in R6 for SE3. And what are those vectors going to be? Well, we see from this most general representation of what these xi-hat matrices are. We only have 2 vectors that are deciding, what's gonna happen, right? We have this velocity and we have this omega. All right. So what we're gonna do is just extract the essential info from this xi-hat matrix that helps us generate our transformations. All right. So we're going to say that if we extract all the information we need, we're going to get this vector xi, which is just equal to this velocity vector stacked on top of this angular velocity vector. And that's going to be a vector in R6, right? And what this is, we have this velocity, or in some cases, the component of velocity is in R3. Then we have omega also in R3. So in some cases, omega is an axis of rotation, and in other cases, it's just going to be the zero vector when we don't have any rotation going on, okay? So sometimes 0, 0, sometimes an axis, right? Yeah, exactly, yeah. So 0 is translation. All right. So what do we call this vector? This vector is called a twist. All right. So if we ever specify a set like xi-hat and then some amount theta, or xi and theta, all right, where we give both a twist for a rigid body and like a displacement, which is either like a linear amount that we're moving for the translational case. Remember, like we said, theta was the distance in the translational case, or it's going to be an angular displacement for the rotational case, right? This will entirely define some rigid body transformation, G equals E to the xi hat theta in SE3. So we're going to be able to represent this entire transformation G, this whole 16 element matrix, using this 6-dimensional vector coupled with some amount of movement theta. All right. And these are called the exponential coordinates. Exponential coordinates for SE3. All right, this pair. Great. So this is a pretty important concept right here. So we're just gonna wait a sec for you guys to copy it down, or just if you have any questions about like this whole sort of process that we've done here. Yeah.
Since V and omega are both unit vectors and theta is shared between them, does that mean it's translated and rotated at the same rate?
So that's a really good question, actually. So it turns out that V and omega are not always unit vectors. So let's talk about the cases where they are. Let me do that up here. So omega is a unit vector if, and then V is a unit vector if. So if we have the case of like rotation, pure rotation, or actually let me say non-zero rotation, and then pure translation. All right, let's split that up in the table. So for the case of non-zero rotation, when we have some rotational motion, then omega will be a unit vector, but V does not have to be. And the reason for that is that we defined, for this case of pure rotation, we had V equals negative omega cross Q, right? So Q could be any point, right? So since Q can be any point and omega is this unit vector, this is not necessarily going to be a unit vector. Oh, sorry, so that's non-zero, yeah. Right, so we have at least some amount of spinning motion going on. Now, for the case of pure translation, omega is going to be 0 since there's no spinning happening whatsoever. But in the case of pure translation, V will be a unit vector since we just want it to be some vector pointing in the direction where we're going, all right? So in that case, V will be a unit vector. So we just try to split it like very cleanly down the middle into these two cases of one where we have some rotation going on, in this case non-zero rotation, and one where we have just translation going on, because really the twists end up being quite separate for those two cases. All right, yeah.
So if we had not like because we just know that like the pure juxtaposition of like non-zero rotation, non-zero, or pure rotation, pure translation.
Mhm.
We had something in between. We can see like I guess like inversely proportional, or it doesn't be like what you like start to go.
Yeah, so a little bit like that. So we're going to come up with this term called pitch that helps define like the ratio of how much like translation is happening with respect to rotation, and that's going to be when we get to screw coordinates. So we're going to see like sort of that inverse relation happening, but it's not always going to be like directly proportional. There will be like some scale factor that goes on. Yeah.
What was the what was the interpretation of W role of B with non-zero rotation?
So V for non-zero rotation. So for non-zero rotation, for the case of pure rotation, we remember that the time derivative of our point was equal to omega cross that point that we care about minus omega cross times Q, which was the distance to the axis, right? So we know that this is taken care of by omega hat times P, and we know that this is taken care of by that extra 1 in homogeneous coordinates. So for the case of pure rotation, V equals negative omega cross Q. So it's like that leftover amount to get like the actual velocity of the point in space when we're undergoing a pure rotation. So it's whatever part of velocity is not taken care of by this omega hat B. So like if we have a point like over here, and this is like rotating around this point, right? We know that our overall velocity will be pointing in this direction. So that's our V overall, which equals P dot. Or let me just clarify. This will be P dot because V and P dot, I don't want to mix them up here. So this will be like our overall P dot. Now we might have something like let's see, so that's our V like going up in that direction. So we might have something like one of them is pointing over there, like that's omega cross P, and maybe that's like negative omega cross Q. So when we add them together, we end up with this total velocity vector. Does that make sense?
That isn't changing.
In this case, it's going to be constant if we have like a fixed axis of rotation. Yeah.
I was just wondering, like, how do you, so you have a matrix for a pure rotation, and you have one for pure translation, right?
Right.
You just multiply those two together to get a.
Yeah. That's a really good point. Like if we had like a G rotation times G translation, that would give us like a G rotation and translation, right? So like we could have like E to the xi hat r theta r times E to the xi hat t, like theta t. And that would be a totally valid way of giving a combination of rotation and translation, right? So that's going to be a function of theta r and theta t. But what we're going to try to do in just a sec is we're going to try and represent both of these with a single xi. Single xi. And a single theta, right? So we're going to try and search for some sort of vector out there that will allow us to represent both of those at once, just using a single transformation. Okay, sure. And this is what the screw is. Yeah.
So I guess kind of like around the same subject as he was talking about. I know before we were talking about the G was equal to like R and E and G.
Yeah, sure.
Which was I think it was to describe rotation and translation in one single digit.
Exactly. Yeah.
So wasn't that the whole point of what we were doing?
Yeah, that's right. So when we do like for translation, we ended up finding like P at some distance theta is equal to E to the xi hat theta times P at the distance 0. And what that means is that this is the transformation G of shifting by theta in direction V. So this E to the xi hat theta, this is a rigid body transformation. Body transformation G in SE3. And there's actually a formula that you could use to calculate out what the value of that exponential is in this case. And that is E to the xi hat theta equals the 3x3 identity, I3, then V times the distance that we're traveling, and then a 0 and a 1. So then this ends up following the format like RP 0, 1 in that case. Like our rotation matrix is just the identity. Then our translation vector is a translation by amount theta in direction V, and then 0, 1, which is followed.
And I can use it.
Right. So this I3 is just the 3x3 identity. So it's the rotation of doing that.
Gotcha. So we have yet to develop rotation.
Yeah. So that one is quite a bit more like messy in form. So if we do the like general case, that'll look something like E to the omega hat theta, 0, 1, and then we'll have like an I minus, I don't know, there's going to be like some term in there, and then there's something, and I think it's plus like omega transpose like V theta or something like that. It's a real mess for translation. Yeah.
Yeah, I was thinking like, so, when we represent both of them as one, are we constrained to being able to translate only the direction of rotation, the axis of rotation?
Yeah. So it turns out that we'll actually be able to find an axis in space that will correspond to any arbitrary rigid body motion. So we're always going to be able to find some axis such that rotating and translating about that will give us anything in space. It's pretty cool. That's called like it's like Shaw's theorem.
That's how we do the satellite problem.
So for the satellite problem, you could just use the pure rotational case. Yeah. So as long as you find that twist xi hat, the good thing is the satellite problem is that the axis of rotation goes straight to the origin. So if you're looking for a point on the axis of rotation, you could just use 0, 0, 0, and a lot of terms will drop out because of that. Yeah. All right. So I just want to make sure that we're able to get to screw coordinates, because I think that's pretty important. Let's see. All right. Yeah, so how do we deal with, by the way, I know half of the class still hasn't submitted the homework, so if you're still working on it, don't worry about it at all. So how to deal with how to deal with rotation and translation.
Yeah.
I gotta go to my midterm, man. I'm sorry. Rotation. Translation. Yeah, I don't think anyone's using the room, so like as long as no one comes and kicks you out, you stay. So yeah. All right. So how do we want to deal with these at once? We're going to use something called a screw motion. A screw motion. Okay. So what we're going to do is we're going to try and find some vector, some twist, xi hat in R6, such that e to the xi hat times theta will give us any arbitrary g in C3, right? Where this is anything. Okay. What's that going to look like? How are we going to do that? So our basic idea for this is that, all the way at the beginning, we said that every rigid body motion out there, right? It's a combination of rotation and translation. So what a screw does, something called screw motion, is we're going to split it up into those two basic components, all right? So first, this is parts of screw motion. First, we're going to rotate by angle theta about an axis omega, all right? This is going to be a unit axis. The magnitude of omega equals 1, all right? And then secondly, we are going to translate along that axis omega, by distance d, all right? And we'll see how we'll be able to figure something out that will allow us to convert between theta and d very easily. Just make sure that we're only going to have like one value up there, all right? So we want this to be the only thing controlling distance, all right? But at the moment, we have this problem where we want to control this length that we're moving independently. We'll see how to deal with that in just a sec, all right? So what does the sort of screw motions look like? So I have this little demo here. So it's kind of funny. Like I was working on these notes for this, and I was like, okay, that would be pretty fun if we actually had a screw, because I found like this tiny screw during office hours yesterday, and I was like, yes. And I was like, today I gotta find a big one because there's more people. So I went down to Invention Lab. I just found the biggest ball that they could find, and then I just taped some cardboard to it. So that's our reference frame right there. But basically, the idea is that we're doing some rotation, and at the same time, that rotation is allowing our coordinate frame to like move upwards in space. So we just saw that we moved up on the screw, right? If you spin it the other way, we are moving like back and down, all right? So we have this combination of moving up along this axis, right? Translating along this axis and rotating about this axis in space. Now, the reason that this is able to cover everything in space is that, say you want to go down here, right? This is just as simple as reorienting our axis and then just translating by some different amount, right? So using this sort of representation, we'll be able to get to anything in space. Okay, so let's sketch out what that looks like. And I'll leave this in the lab downstairs. If you guys just mess around with it afterwards, it's kind of fun. All right, so what does this look like? Okay, so we have our axis omega. Just draw this a little bit bigger and a fun color. So out there we go. We have our axis omega. And to start, remember, we're going to start out by doing a rotation about that axis. So let's say that this is our point P that we care about, okay? And that this is a point Q on the axis. And we're going to rotate about that axis first. All right, so P is sort of going to like sweep out this little cone here around this axis. All right, this is going around. So we perform this rotation by some angle theta. And where does that end? So let's say we rotate by this theta, and we end up at this point P prime. All right. So we've done our rotation. Great, we're at our rotational orientation that we want. Now what I'm going to do is I'm going to shift this entire thing up by some distance d. All right. Now where does this bring us? I'm going to bring this entire rotated cone up. And that's going to bring this point P prime to this new shifted point P double prime. Okay. So we moved along omega by this distance d. We rotated about omega by this angle theta. Okay. So this is what a screw motion will look like in space. Do we have any questions just about like geometrically what this screw is doing, or like what how do we feel about the screw? Pretty good. All right, cool. So how do we find the twist for this, right? Our whole goal was to find this one xi hat that's able to encompass everything that we need to do. All right. And we're going to figure this out by splitting it into those two cases that we just discussed, right? One with this pure rotation, one with this pure translation. Okay. So first, what's the twist for the rotation that occurs? All right. So we're going to use our knowledge of rotational twists from earlier. And we know that for this first action that happens, the rotation is one in green, we are going to have the following twist. Xi rotation equals negative omega crossed with q and omega. Remember that this term in the top was the leftover term in velocity. And velocity after doing omega crossed with q, or omega hat is how we wrote it. Okay. So this is our twist for our rotation. This is exactly what we derived above for the case of pure rotation. All right. So now, how do we deal with the translation? Well, this is where we sort of run into a problem, right? Like if we have e to the xi hat rotation times our angle of rotation, sure, that gives us rotation by theta about the axis omega. But if we just do what we had done before, right, where we just have this, unit vector v, right? So xi translation equals v and 0. And we just point it in the direction where we want to go. We say v is a unit vector. It's pointing in the direction of omega. I'm just going to multiply it by this theta and it's going to work out. That's not going to give us what we want, right? That's going to give us a translation of an amount theta, right? So then we'll be rotating by theta along around this axis. And then we'll be translating by theta along this axis. But we don't want to translate by theta. We want to translate by this other distance d, all right? So we need some way of converting between theta and the distance that we want to go, okay? So we must convert between the angle we rotate, theta, angle we rotate, and the distance, d, we want to travel. Okay, because we know our direction of translation will be equal to, will be equal to omega. So we're still translating in that direction, but it can't be a unit axis because it's not going to give us the correct amount of translation. Okay. So what we're going to do is to define this term called h. This term is called the pitch of the screw. So h is equal to the amount that we want to translate, d, divided by the amount of rotation about that axis that's occurring. All right. So what this does is that it gives us a twist, a translational twist of d over theta times omega and a 0 beneath it, okay? Which is equal to h times omega with a 0. So that way, when we go ahead and we multiply this twist by our angle theta, right? This is going to convert it to the distance that we want to go, and it's going to do that for us, right? It's going to be d over theta times this direction that we want, multiplied by the angle that we're rotating, right? Over 0. This angle and this angle are going to cancel out. And it's going to give us a translation of d along the direction that we want, which is omega, okay? So what this pitch does is it converts the amount of rotation that's occurring about that axis to the amount that we want to translate along that axis, all right? And you can sort of see this in this screw example. So if you go and you like buy a bolt from a store, and you buy a like an imperial bolt, what they do is they specify like the diameter, and and they specify the pitch. So they actually tell you how much rotation about this axis will correspond to how much translation. So for example, if I do one full rotation about here, like there, back around to there, how much did this move down? That's going to be the pitch. Okay. So for screws, if you're just, I don't know, out of interest, usually they specify it as the distance between these threads on here. So for one full rotation, like how many millimeters or how many inches that I move up over one full rotation, that's just like doing d over 2 pi in our case for our pitch calculation. So, yeah. Good at this homework. All right, so we have this pitch, we have this direction. Now all that we need to do is bring together this translation and this rotation. All right. So to find our overall psi, what I'm going to do is I'm just going to add up our translational psi and our rotational psi. What's that going to give us? It's going to give us negative omega cos q plus h times omega, right? And since we have this h omega up here. And underneath, we're going to have our axis of rotation, omega, okay? And this is our final formula for a general screw motion. Screw motion with non-zero rotation. With non-zero rotation. Okay, so bear in mind, there is always some rotation happening here. If we had zero rotation and omega was just equal to 0, this formula wouldn't work, right? Because omega would drop out to 0, this would drop out to 0, this would drop out to 0. We would end up with a 0 vector, which doesn't give us anything useful, right? So for the case of non-zero rotation, this psi will give us everything we need. Okay, so the transformation of rotating about omega by angle theta, and then translating along omega by distance pitch h times theta is as follows. G equals e to the z hat times theta. All right. So by taking the exponential of this twist, we're able to figure out these general transformations that both rotate and translate. All right. Yeah.
Could you clarify the terminology of screw versus twist? Because I'm sure they talked a lot about like going between the two.
Yeah, sure. Yeah. So when you ask for screw coordinates, usually they refer to an axis, which is like your screw axis in this case. Okay. So it's your axis omega. It's the magnitude, which will be the distance you translate. And the angle you move. All right. So when they ask for like the screw coordinates, this is usually what you would give. So you give the axis, the magnitude, distance you travel, and the angle you move. I think on the homework, even if it says like screw coordinates, I'm pretty sure in the answer key, they have it either way, that if you just give the exponential coordinates, that'll be all right. But if you just ask like for the exponential coordinates, then we're asking for this twist psi and this angle theta. Okay. So psi in this case is this R6 vector. Okay. It's not the matrix.
So just to clarify, magnitude is
yeah, so you just give that as a pair. Yeah. So like
it was still 3 though, right? It was like axis magnitude.
yeah. So axis, magnitude, and yeah. So I think I don't know. Like in the textbook, they have it where you give like the axis, like the distance and the angle or something, and then some of them, like some slides I've seen, like axis, magnitude, pitch. But I think as long as you give like 3 non-redundant parameters, then you'll describe the screw. I would just go with whatever convention you learned in lecture, and then just stick with that on the assignments just to be safe. Yeah.
Who's the motion as the twist?
Yeah, that's a good question. So in general, like a twist will be like the quickest way to get, I guess, like a clear representation of a general rigid body motion. Like if we're doing a pure rotation or a pure translation, then it's very easy to get the twist for that, just using the axis or like the direction of motion, right? But if we want to represent them both by a single transformation, just for whatever reason. Maybe that's just something that we want to do. Then we would use a screw in that case. What about a real world application? I'll be honest, I don't usually use exponential coordinates. Like I usually just use like the rotation matrix and the point directly, because a lot of times that's what like if you have like a motion tracking system, that's what will be published by the data. But for the lab, in this case, where we're working with a manipulator arm, in that case, I think the twists are generally what I use. Yeah, but they're pretty interchangeable concepts on the whole. Like they're really referring to the same vector because they're both these 6D vectors that when we apply the exponential, they give us a transformation. Yeah. Yeah.
Just to clarify, like pure rotation and pure translation, those are twists. And then
so you could represent both of them with either one. So this idea of a screw is just, like a geometric interpretation of what a twist is. So really they're referring to the exact same thing, just this idea that we could generate a transformation with a 6D vector. They're just different ways of looking at what that vector is. Yeah.
So really, let's define what
yeah.
a transformation that's both translation and rotation. The approach kind of is and it's all the smooth part of which from there you
yeah, exactly. So you would like get your xi first and then your angle of rotation theta, like using this formula right here. So you would figure out your xi and then your angle of rotation, and then you would provide that as your answer instead of giving the magnitude, the distance, and so on. Yeah.
You would have the first one.
Yeah. Yeah. So just to clarify for like the pitch, like if you rotate by like pi, but you want to translate like by 1 meter, your pitch would be h equals 1 over pi, right? It's just the amount you want to go divided by the amount you want to rotate. I think this is actually the pitch for one of the problems in the homework. It might be 2AA or something like that. Yeah. Yeah, let's see. Is there anything else that I wanted to cover? So in general, I think that is all that I had for you guys here. Yeah, do you have any other questions just in the last like 5 or so minutes?
one quick question.
Yeah.
The axis, if there is a pure translation, it will be the axis of the.
Oh yeah, that's a great point actually. So for pure translation, what is the twist? Or what is the screw? So in this case, we say that the pitch h is actually like infinite. Okay. And the reason for this is that for 0 rotation, we're still moving, right? So 0 rotation still move. And the idea of it being infinite, like just comes from the formula for pitch, where h is like d over theta. Like if we let theta approach 0 in the denominator, this is going to start blowing up to infinity. Okay. So in this case, we're going to use a slightly different representation, which is, as you mentioned, just the direction. So for pure rotation, or excuse me, for pure translation, we're just going to use that pure translation twist that we derived earlier for the screw as well. So it's just going to be v and 0 for omega, where v is just the unit vector in direction of translation. Okay. And then in this case, theta will just correspond to the amount of translation. So all that you need to keep in mind for the screw in this case is that the pitch sort of tends to infinity. Yeah. All right. Are there any questions on Zoom? None. Okay. Yeah. How do we feel about this in general? You good? Nice. That's a good sign.
I think it's possible that homework content-wise could like fall 1 week behind so that this discussion could help with it.
Right. Yeah.
Like has the work content-wise 1 week after. So
Okay. Yeah.
like the same week that the content is taught, like not a whole bunch of questions that are